Hello everyone, my name is Brandy. Today I am going to be talking about some work that was submitted as an extended abstract to the 7th Thermal and Fluids Engineering Conference, which is going to be happening in Las Vegas. I'll be presenting this again on May 17th there. We're going to be talking about waste heat and its role in decentralized produced water treatment in the oil and gas industry. So today we're going to go over some background of what produced water is, some of the motivation that we have for picking the treatment technology that we have and for looking at waste heat storage in the first place. And then I'll go briefly over some of the methods we used in modeling the waste heat through the system and then onto our results. So let's start with the background. We focus our research on the Denver-Julesburg Basin in Colorado. Most of the activity in this basin actually shows up in Weld County, so we even limit ourselves further. We focus on Weld County oil and gas development. So what is produced water? Well, first a well is drilled and hydraulically fractured. And then the production phase begins where we produce oil, natural gas, and produced water. This produced water can be super salty, up to 10 times the salinity of seawater. So it's really more of mud that comes up, and we have to desalinate it, and it's the hardest part of treatment for produced water. We also want to point out that a significant volume of the total produced water from any well comes back within the first 2 months of production. So that's the time that we focus on where there's a demand for treatment. So how much produced water is produced? Well, during hydraulic fracturing, we can see up to 11 million gallons being used on a single well to be hydraulically fractured. And in Colorado, around 2010, we saw a huge boom in oil production in horizontal wells being drilled. From 2010 to 2020, we saw a 337% increase in the amount of oil produced. And we actually saw in 2020, 11.8 billion gallons of produced water coming up out of the ground just in Colorado. So why do we want to treat this produced water? Well, what happens to produced water now? Because produced water is so difficult to manage, because it is so saline, such dirty water, we actually inject most of it into disposal wells. So one of the reasons that injection is not a sustainable option is actually induced seismicity. So these graphs are from a study done at Virginia Tech in 2014, where they looked at the boom in Oklahoma that happened about the same time as in Colorado in about 2009, 2010, and they started to see increased seismic activity, earthquakes, around disposal wells, and those are shown up in the map. The red are earthquakes and the black is disposal wells, and as you can see in the bar graph on the bottom, the amount of seismic activity that they were seeing was significantly increased after that boom. The other option is treatment, where we can desalinate this water and hopefully have a water which is a high enough quality for discharge or even livestock watering or irrigation activities. So how did we come to the treatment technology that we did, which was membrane distillation? That's what we picked for desalination technology. First, let's go through some of what the options are. First, we have reverse osmosis. This is typically what is used for desalination of things like seawater. However, it's limited to a pretty low salinity brines at a maximum of 70,000 ppm. Some of the water that we're talking about can be up to 300,000 ppm, so doesn't quite hit the range that we need it to. Another option that most people think of first is direct evaporation of water. What if we just boil the water out of the rest of this sludge? And that's pretty energy intensive. So we don't want to do that. So the next option is mechanical vapor compression, which is the state-of-the-art technology for desalination of brines over that 70,000 ppm. Energy consumption for MVC is actually pretty low. We see a gain output ratio of 15 to 20, which means that it's doing 15 to 20 times better in terms of energy consumption to produce the same amount of water as evaporation would. The problem with MVC is that it is electrified, and we do not have electricity delivery infrastructure on site for a treatment facility. So that finally leaves us with membrane distillation. It has a GOR of about 2. So unfortunately, mechanical vapor compression does do about 10 times better in terms of energy compared to membrane distillation. However, MD is thermally driven, which means that we can use heat to power this treatment system. So why do we use waste heat storage? So where is this heat available? And we looked at waste heat, which is essentially just heat that is wasted during engine operation and pumps operation, just not used and just rejected to the atmosphere. So if we can collect that, that'd be great. And we identified 2 sources of waste heat that could supply energy for treatment. First being on site is hydraulic fracturing, where they have huge pumps which pump water down underground and fracture that ground to enable oil production. However, hydraulic fracturing does not happen at the same time as treatment demand is when that water is coming up out of the ground. So we would have to store heat from when hydraulic fracturing happens to when produced water is coming out of the ground. Second option is off-site. Natural gas compressor stations, huge engines that are constantly producing waste heat. However, they are not on site, so we would have to move either the water to the natural gas compressor stations or waste heat from the natural gas compressor stations to the well where the water needs to be treated. So how does storage help us? Right, the typical scenario that people are looking at right now is taking produced water and moving it to a natural gas compressor station where there's constantly waste heat available for treatment. We're looking at 2 other options. The first being taking waste heat from hydraulic fracturing, storing that over time, and then treating water on site as it is being produced. And the second option is collecting waste heat from natural gas compressor stations and actually transporting the waste heat instead of transporting water. Transporting that heat on site, again, to treat the produced water as it is coming out of the ground. So how did we analyze all this? Well, there's 3 main storage materials that we looked at. The first being sensible storage materials, which have an increasing temperature as we have more energy in them, meaning that as we remove heat during the treatment process, we're actually decreasing the temperature of that waste heat and possibly impacting the treatment technology. Phase change materials, again, have that temperature drop as energy is removed. However, there is a little bit of a constant temperature range, which enables more energy to be added and removed from storage. And then the third material that we looked at were thermochemical materials, which have constant temperature charging and discharging and enable us to have a consistent performance out of our treatment technology. So how does membrane distillation perform as treatment goes on? So we see that the temperature is dropping, and as that is happening, the energy consumption, specific energy consumption of membrane distillation is significantly increasing. So we know that we want to have the storage material at the highest temperature for the longest possible time to make sure that we have the lowest energy consumption possible out of our treatment technology. We also, because of this change in the performance of membrane distillation, we have created a new metric called apparent specific energy consumption, which just takes into account the entire performance operating time. We take the total amount of waste heat over the total amount of produced clean water, and that's our parent specific energy consumption. So our system model, for charging, we just look at how much waste heat we have at a given well, and divide that by the enthalpies of the start and end temperatures. We assume it starts at 20 C and we're heating it up to 90 C as our waste heat source temperature. For discharging, we go through discretized time stamps, which for each step we calculate the amount of heat that is removed from the system, from the heat storage system, and then calculate the temperature of the waste heat storage system after that time step, and repeat until we get either full treatment of produced water or we use all of the waste heat that we can. So what do we learn? First, let's actually look at the wells that we looked at in Weld County. We identified 3 wells really that had different ratios of waste heat availability and produced water coming out of the ground. If you have, say at the Vera well, there's a lot of produced water coming out of the ground, but not much waste heat being produced. On the other hand, the ratio for amount of waste heat to produced water is much greater at the Peterson well, where there's a ton of waste heat being produced, but not so much water that needs to be treated. So what happens with on-site waste heat storage? First, we can see that some wells, like the Vera well, which has a lot of water that needs to be treated, but not a lot of waste heat available, uses all of the waste heat that it can. Other wells treat all of the water that it has available. It just has excess waste heat, so it treats as much water as it can. And again, in the average case, we see apparent specific energy consumption can be about half of direct evaporation, which means that we're hitting the optimal empty operation of a GOR of about 2. Waste heat transportation, our second option. So we looked at the volume of waste heat storage material compared to the amount of produced water that it was treating. And we actually saw that the number of trucks needed for transportation could be decreased by up to 70% if the correct storage material were used. So that's the end of the slideshow and presentation today. I just want to send out some thank yous to advisors and colleagues. First off, Todd Bandhauer, and then TJ and Garrett, Jason and Christian. Thank you so much for helping in this work. And then shout outs to the National Science Foundation and Interfuse program and Reach CoLab at Colorado State University. All of these people contributed so much to this project, and I thank you so much. And if there are any questions about any of this work, please just contact us. We are happy to talk about what we have done. So thank you again, everybody.